Hey guys, here's 6.4, which is the polar coordinate system. It's a pretty easy lesson, so hopefully you'll understand it, and the real fun comes in 6.5. So in 6.4, the main goals are that we're going to just convert back and forth between the rectangular and polar systems for both coordinates and equations. And so you might ask, well, what is the polar coordinate system? I'm so glad that you asked. So the rectangular system, also known as the Cartesian coordinate system, is what you're used to seeing, the two-dimensional, right, like rectangular system. It's called the rectangular system because for any point, let's say this is the point 3, 1, the x and then the y, look at that, like it makes a rectangle. Yes, so it's called the rectangular coordinate system. The polar coordinate system, you could represent the same point, but the polar coordinate system is based off of a pole, which we locate right here at the origin, and then the radius out from the pole and the angle. So instead of giving the x and y coordinates, instead we're looking at theta, which is the angle, right, from standard position, and what r is. And so for any xy coordinate, let's say this is just the coordinate xy, then how are x, y, r, and theta related? This is something that we already did because we did it with vectors. So that's why this is fitting that it comes in 6.4. You can see from trig that if here's the x coordinate and here's the y coordinate, that we can get r, because we know that r squared equals x squared plus y squared. And we know that the tangent of theta is y over x. These should be on your paper plate already. And so feel free to use that. That would be how we can find x and y. Or sorry, we can find r and theta if we have x and y. Okay, so then if I have the r and the theta and I want to find the x and the y, I can look at the trig ratios and I can say, okay, well, the sine of theta would be y divided by r, and then multiply both sides by r, and you get y equals r sine theta, and x similarly equals r times the cosine of theta. Those should also be on your paper plate. So these four equations are going to convert you back and forth. Here, this is going to convert from polar, if you already had polar, to rectangular, and these would give you the rectangular to the polar using those, more or less. Okay, so let's go ahead and see what we have. First, we should just be able to plot points. Think about pre-algebra when you were first learning the Cartesian coordinate system or the rectangular system. You had to do things where you just graphed points. So that's what we're going to do here. The polar coordinate is given by the r first, and then the theta. This is actually a little bit different than we're used to seeing with xy, because with x and y, the x is the independent variable and then y depends on x. But with r and theta, when we make equations, r turns out is going to depend on theta. So r is the dependent variable and theta is the independent variable. And so the order that they're written in the coordinate pair is just a little bit backwards from what you're used to seeing. Just a heads up on that. So for point P, notice it has a radius of 2 and an angle of pi thirds. So I'm going to go up to pi thirds. Sorry, this is in degrees, but you can do it. And then I'm going to go out to a radius of 2 units away from the pole. So this needs to be bigger so we can see what we're doing. So pi thirds and then a radius of 2 would take me to this point right there. And then I can label that that's point P. Hopefully that makes lots of sense. Okay, so then for Q, notice that the radius is negative. What do you think a negative radius might do? Turns out we're going to go to the angle 3 pi fourths, which would be this angle right here, right at 135 degrees. But then instead of going a radius of +1, which would land us there, we're going to go a radius of -1, which kicks it 180 degrees the other side of the pole, and gives me this point that's right there. And so that would be point Q actually lands in quadrant 4 there. And then for point R, notice R has a positive radius, but it has a negative angle. We already know how to do negative angles. Negative angles just means you go you go clockwise around the circle instead of counterclockwise. So I'm going to go to the angle of negative 45 degrees, and then out to a radius of 3, and then that would be point R. So you might be thinking, or maybe you might not be thinking, but let's try and compare these systems. The polar coordinate system has a little bit of an issue, and you might be able to see it if I would ask you to plot the point to 7 pi thirds. So if I go to the angle 7 pi thirds, which would be all the way around once and then another pi thirds around, and I go up to a radius of 2, you can see that that's going to land at point P. So that location on the plane could be represented by point P, or we can call this one P prime. Those are two different coordinates, but they represent the same spot on the plane. And that's a problem. I mean, it's not ideal. The rectangular system does not have that issue. If you're looking at the point 3, 1, that's the only coordinates that you can use to represent that point. Whereas here, it's not. So P prime would land at the same spot. Or let's think of how else could we land there. We could land there by making the radius negative 2 with an angle of pi thirds plus pi, right? So 4 pi thirds would take me to an angle in quadrant 3 down here, but then I'm going to kick it back because of the negative radius, and so that would land at the same point as well. We also could do P triple prime, just for lack of anything better. And we could say, what about if I had a negative angle? If I had a negative, so a positive radius, but a negative 5 pi thirds angle, that would also land at the same spot. And so these are not unique. Now, I'm not allowed to just change the pi thirds to 60 degrees and say that that's a different representation. That's actually not a different representation, that's just changing units. Whereas all of these are actually keeping the units the same and simply changing the radius or the angle. Okay. So because they are not unique, turns out that there are infinite coordinates that can be used to represent any one location on the plane if you're using polar coordinates. So it says find all polar coordinates for P. And so we can say, all right, well, what could I do with P if it's 3 and then pi thirds? Well, I could keep the radius the same, and then I could keep the angle the same, but I could add as many full circles as I want to that. So I'll slap a plus 2 pi k on there, which means I'm adding as many full circles as I want to that. And then I also could say, okay, well, if I make the radius negative, then I would have to add 180 degrees or pi to the angle, and then that would kick back and arrive me at the same location. So that would be negative 3 4 pi thirds would be the same location, but then I could add as many full circles as I want to that as well. So that would also be plus 2 pi k. And so either one of these well, both of them combined is what we need if we want to find all of the polar coordinates for P. Next, converting between the coordinates. This is where we're going to use those 4 equations that we just talked about at the beginning of the lesson. So in this case, we have the polar coordinates and we're looking for the rectangular coordinates. So I know that x equals r cosine theta. So that would be 3 times the cosine of 5 pi 6. And y would equal r times the sine of theta, which is 3 times the sine of 5 pi 6. And I could type those in my calculator, but I don't need to because 5 pi 6 is on the unit circle. So the cosine of 5 pi over 6 is negative root 3 over 2. And the sine of 5 pi 6 is 1/2. And so point P, if I convert to rectangular, becomes -3 root 3 over 2, comma, 3/2. Hope that makes sense. You can do the same thing in B and just leave the negative attached to the angle. You don't need to change the angle and make a positive coterminal angle. It would just be 2 times the cosine of -200 degrees and then 2 times the sine of -200 degrees. But you would need to change that in your calculator to degree mode if you weren't on degree mode. And then that's not one that we could evaluate. I mean, we could leave it in exact form, but if we wanted to evaluate, since 200 is not an angle that's one of our special angles on the unit circle, we'd have to use the calculator to evaluate that one. Okay. What if we wanted to go from rectangular to polar? So then we use the other two. We use the other two equations. So -1, 1, think about it, would be right there. And -1, 1 means you're going left 1 and then up 1. So the radius is just the Pythagorean theorem. And so the radius here would be the square root of 1 squared plus 1 squared, which is square root 2. And the angle, in this case, again, I don't need a calculator for this because if I know that that's a 1, 1, then I know that that's a 45, 45, 90 triangle. And I can look at it in quadrant 2 and say, oh, that angle is 135 degrees. But we're going to use radians because we're more sophisticated. So this would be the point in polar coordinates. This would be the point root 2, 3/4. We normally, even though that there are infinite points that can represent that location, we would pick the easiest one. So don't just start adding 2 pi or making the radius negative for the heck of it. So then go ahead and try the second example on your own if you want. I'll give you pause the video and then we'll start in 3, 2, 1. Okay, so here's -3, 0. So in this case, the radius, which is the distance from the pole, is 3 because you're simply 3 units from the pole. And the angle there would be pi. And so these would just be the coordinates 3, pi. You also could say that this was -3, 0, which is really interesting because that's actually the same as what point Q says in rectangular form. That's a fluke. That does not happen very often, so it makes it interesting that if the radius is a -3, which kicks it to the other side, but the angle is a 0 degree or 0 radian angle, then here's your angle of 0 degrees, but you're kicking the radius backwards because it's negative. And so it turns out that -3, 0 and -3, 0 represent the same point. So that's fun for the day. I want to do one that's not on here. I want to do one that you would have to use your calculator for. So let's think about if we had the point 3, -1, and I wanted to convert that to polar. So that's down here, and I can find the r by doing the Pythagorean theorem. So that's not a big deal. The r would be root 10. However, to find theta, I would have to use the equation that says that the tangent of theta is y over x, which is -1/3. And I would find the inverse tangent of -1/3. If I grab my handy dandy calculator, and we'll stay in radians because we've been doing class in radians for today. So if I do the inverse tangent of -1/3, that would take me to -0.322 radians. So I would have root 10 -0.322 radians. Not a big deal because you're like, okay, yeah, that angle, I can see that that angle is negative. But then, here's where it gets tricky. So what about if I give you the point -3, +1? So with that point, the radius again is root 10. But then if I use the equation, tangent theta equals y over x, I get that tangent theta equals 1 over -3, which coincidentally is the same thing that we had here. So when I put it in my calculator, it's going to give me -0.322 radians. because that's where inverse tangent or arctangent is defined from negative pi halves to positive pi halves. But I know that I'm in quadrant 2. So when you're in quadrant 2 or 3, you have two options. You can either add pi to the angle, or you can kick the radius and make it negative. So at this point, we can make negative root 10 and then negative 0.322 radians. That would be one option. Or the other option, which I prefer, even though it does mean that I have to do another calculation, would be to simply go ahead and add the pi radians to that, because we know that the period of tangent is pi radians. And then that takes me over there. And then I can get that that would be 2.820 approximately. 2.820 radians. Either one of those would be fine for converting. Okay, so we plotted points, we converted coordinates, and now we're gonna convert equations. So in this case, I have r equals 4 secant theta. Turns out for these problems, we just want to get it into the form, into some sort of form that either has r squared in it, because I know r squared is x squared plus y squared, or if I had r times the cosine of theta, I know that that's x, and r times the sine of theta, I know that that's y. And so if I can get it into any of those forms, then I can convert. So for r equals 4 secant theta, then that would be, that's the same thing as 4 divided by cosine theta. And then let's just multiply both sides by cosine theta. So I get r cosine theta equals 4. But r cosine theta is x, and so I get x equals 4. So it turns out this, if we did it right, which you can check on your calculator, would just be the vertical line that we would get at x equals 4, which is kind of crazy, and I hope that it blows your mind, and I'm sad that I can't see all of your faces. If you go into polar mode on your calculator and you graph this, take a look and watch how your calculator graphs it, because it actually will start at theta equals 0, which gives you a radius of 4, and then it moves up like theta equals pi 6, and then you get a radius of 4 times the cosine of pi 6, and then you end up with this point and this point and this point. So it actually starts here and goes all the way up, and then it starts then at quote unquote negative infinity and comes back and finishes there if you graph this. So it's like taking the coordinate plane. So pretend this is the coordinate plane. And it's like taking a positive infinity and negative infinity and going whoop and making a cylinder. So this graph would start here on the x-axis and it would go up. And then guess what? It comes back from negative infinity. So it's like negative infinity and positive infinity are meeting at the back of this cylinder, which is amazing. Anyways, we get x equals 4. And then last but not least, here's a rectangular one that we want to convert to polar. So in this case, we are going to start by expanding everything out. X squared minus 6x plus 9 plus y squared minus 4y plus 4 equals 13. Notice the 9 and the 4 and the 13, I can just subtract 13 from both sides and that goes away, and then I would have equals 0 on here. Don't lose the other side of your equal sign, please. And then let's substitute. I know that x squared plus y squared together, but that equals r squared. And then I know that x equals r cosine theta. And then I know that y equals r sine theta. So I swapped out everything, and now look, I don't have any x's and y's anymore. I just have r's and thetas. So I'm mostly done converting. When I convert from rectangular to polar, I do, if possible, want to get this solved for r. So notice that I have 3 terms. Every term has an r. I'm going to factor out an r out of that, and I get r and then r times, or r minus 6 cos theta minus 4 sine theta equals 0. Notice I'm not dividing by r. When you divide, you can lose a solution. Don't divide by a variable ever. However, then the zero product property says either r equals 0, which I know is just, if the radius equals 0, then I'm at the pole, which would just be 1 point at the origin, which is not what I'm looking for here. So I can have r equals 0, but guess what? That's not the right one. I have this one would equal 0. And so if that one equals 0, that factor equals 0, then we have r would equal 6 cosine theta plus 4 sine theta, because you're just adding those two terms to the other side. And so I'm getting excited, throwing my stylus around. So there you go. So r equals 6 cos theta plus 4 sine theta is the same equation as what this equation would give you. And then what shape would that be? Let's think about it. Hopefully, you know that this is a circle of radius root 13 that's centered at the point 3,2. So if it's radius of root 13, then turns out it goes through the origin. And you can also make some parallels or some conjectures, some connections between the fact that the center here is 3, 2, and how is 3 and 6 and 2 and 4, like, how are those related? I don't know. You might be able to make a conjecture there. So that's it. I believe in your homework you have one that's like the same thing as this, but backwards. So you should be able to go backwards from this one or backwards from the other one. And have fun doing your 6.4 homework. And I'll see you in office hours potentially tomorrow.